Okay, so now let's look at related rate problems. Related rate problems involve using a known rate of change to find an associated rate of change. The 3 steps to problem solving are to first understand what you want, what is it you're looking for. Second, determine what you know. And third, find a connection between the two. Okay, so here we have our steps listed in order. Right? So they're just basically more detail on those 3 things. Finding what we're looking for, what do we already know, and what's the connection. Right? So to be able to do those things, the first thing we're going to do for our related rate strategies, and these are in your notes, is to draw a picture. Right? That picture is going to be real important to see how variables relate to one another, how variables can be rewritten, determining what we know, what we need to find. So we're going to draw a picture and name the variables and constants. We're going to use T for time because all of these things change with respect to time. They're taking place over time. There's change over time. Assume that all variables are differentiable functions of time. So since we're differentiating with respect to a different variable, right, we're differentiating our variables with respect to time, we're going to be using implicit differentiation to solve related rate problems. Second step, we're going to write down all the numerical information that we have in terms of the symbols you've chosen. Oh, it looks like I'm missing a parentheses there. We're going to write down what we're asked to find. Usually it's a rate expressed as a derivative. Anytime we're talking about rates, we're talking about derivatives. And we're going to write an equation that relates the variables. You may have to combine 2 or more equations to get a single equation that relates the variables whose rate you want to the variables whose rate you know. And when we're talking about equations, often they're going to involve common equations from geometry or algebra. Like, for instance, the area of a circle, or the volume of a cube, or the volume of a prism, or Pythagorean theorem. You'll see a lot of those formulas that you've used in the past be used here when we're solving related rate problems. We're going to differentiate with respect to t, then express the rate you want in terms of the rate in variables whose values you know. Okay? So we're going to write an equation, and then we're going to differentiate that equation. And it's going to be with respect to t. So anything that's not a t, right, is going to have to include implicit differentiation. And then we'll evaluate. We'll use the known values to find the unknown rate. That 6th step, that's when you can substitute values for constants. Okay? That's when you can plug in values. Right? Do not plug in any values until you differentiate. So first we differentiate, and then we plug in values. Okay. All right, so here's our first problem. Okay. So here's my picture. Right? A pebble is tossed in the water. Right? So that's supposed to show the ripples there. Right? So if you throw something in the water, how the ripples spread out, that's what my picture is showing. The radius of the ripple is increasing at a rate of 6 inches per second. What's the rate of change in the area enclosed by the ripple? All right, so what we want to know is right here. What's the rate of change in the area enclosed by the ripple? Okay, we want to know the rate of change in area. Okay. In other words, we want to know the dA dt. We're given the rate of change in the radius of the ripple. Right? So we're told here that, let me use a different color. We have the radius is increasing at a rate of 6 inches per second. Okay? So that's 6 inches at 1 second. After 2 seconds, it's 12 inches, and so forth. Right. So we're given a rate of change in the radius of the ripple. We also know the formula for the area of a circle, right? The area of a circle, pi r squared. Area equals pi r squared. Since area is expressed in terms of the radius, you can take the derivative of the area equation with respect to time. Okay. Let's take a look at this problem a little bit more. Right, here's our problem here. So dr dt, this is the rate of change in the radius with respect to time. this down. Okay, so same problem. Pebble is tossed in the water. The radius of the ripple is increasing at a rate of 6 inches per second. How fast is the area changing 2 seconds after the pebble is thrown? So 2 seconds, that's our time. Okay. We can find our radius just by recognizing that our radius is going to increase at a rate of 6 inches per second. So 1 second, we're at 6 inches. And 2 seconds, we're at 12 inches. And 3 seconds, we'd be at 18 inches, although we don't care because we're just asked for 2 seconds. How fast is the area changing? Okay, so we know the time, we know the radius, and we know the rate of change in the radius. What we're looking for is dA dt. How is the area changing? Okay. We know the radius is increasing at a rate of 6 inches, and radius and area are related using our area formula. Now, very important, you want to take the derivative first. See, we have these values here. We are not going to plug any of those in until we take the derivative. Right? So we're going to differentiate our equation. So the very first step in, well, I can't say it's the first step in the problem solving because we had to get our picture, we had to get our equation, but what to do when we're trying to find our rate of change here, we have to differentiate before we plug in any values. I just want to make sure that's very, very clear because sometimes students try to plug in values first. If you do that, the problem is you're assuming that these values can't change. And we can see right up here that the radius would change. If it wasn't 2 seconds and I waited more time, I'd have a different size of radius. Time can change. The radius can change. The only thing that's not really changing in this problem is the dr dt. But even that won't get plugged in because you can see there is no dr dt in the beginning. All right, so I just want to make sure it's very, very clear that this implicit differentiation has to occur before any substitution. All right, so we have our formula here, area equals pi r squared. That's the formula that relates the radius and the area. That's how they're related. So when we're looking for equations, we're looking for formulas that relate these two values. Now we're going to take the derivative. Okay? Notice that it's with respect to time. Not a single one of these variables, A or R, is t. Right? None of those are time. So we're going to have to use implicit differentiation for all of our variables here. The derivative of area with respect to time would be, so d dt here, this means to take the derivative. Right? But once I take the derivative, dA dt and dr dt, they are the derivative. That's a noun. The d dt means take the derivative, and in this case, with respect to t. We've seen in the past where we had d dx, that means take the derivative with respect to x. We're taking it with respect to t. The derivative of area with respect to time is just dA dt. Right? We're going to use those same variables. This is just saying it's the derivative of area with respect to time. It's an implicit differentiation because we're taking it with respect to another variable. Pi is a constant, right? 3.14 and a bunch of other digits. But r is not. That's a variable. All right, so we're going to use the power rule, right? So the exponent comes in front. So now I'm going to rewrite this. Instead of pi times 2r, I'm going to write that as 2 pi r. And then r is not t, so I need to take, it's a chain rule, I have to take the derivative of pi blop squared, and then I have to take the derivative of the blop, right? The derivative of the blop, the derivative of r is dr dt, because we're taking it with respect to time. Okay? So now we've got dA dt equals pi times 2r times dr dt. We can make that, you can make that be 2 pi or just leave it the way it is. Once I've taken the derivative, now I can substitute values. So differentiate first. Very, very important. Then evaluate. Because these are variables. They're changing, right? Once we've taken the derivative, then we can evaluate it for a moment in time, right? We're evaluating for exactly 2 seconds, right? dA dt is what we're looking for. We know what the radius is. The radius is 12, right? Right here, right here. After 2 seconds, that radius will be 12 inches. The time, the 2 is already there. And then dr dt, we already got it, right? dr dt is 6. Right? So notice we didn't really plug in the time at all, but we used the time to find what the radius would be. Sometimes you have to do that. Sometimes you're just told when the radius is. Okay? All right, so now all I got to do is multiply. So 2 times 12 times 6 is going to give me 144 pi inches squared. We can see that. So that's the rate and change in my area. Right? So my dA dt, the rate, how fast my area is changing 2 seconds after that pebble is thrown, it's changing at a rate of 144 pi inches squared per second. Very important. Don't forget the units. It's not correct if you don't have the correct units. And it's a rate. So when we're finding a rate, it's going to be a unit of measurement per a time measurement. Okay? I'd say you have any questions, but you can't answer me. But you can ask me in class. You can ask me questions in class. All right. So this is a pretty nice, simple one to start off with. Right? We're going to look at some how the problem will change based on what's changing in the problem. Because sometimes not everything changes. Here, the area, if the radius changes, the area is going to have to change, right? You change the radius of a circle, you're going to change the area. Sometimes we can change one thing and not change another thing. Okay? For instance, with the volume of a cylinder. Right? The volume is going to change if either the radius or the height changes. But what if just the radius changes? Or what if just the height changes? Or what if both changes? How does this problem change? It's a different problem depending upon what stays constant and what changes. All right, so here we're looking at the volume of a cylinder. This is the formula for volume of a cylinder. Basically, it's just the area of a circle, pi r squared, times the height of the cylinder. Right? It's like you're stacking a bunch of flat circles. Right, so the radius r and the height h of a right cylinder are related to the cylinder volume by the formula pi r squared h. And so we're going to look at 3 scenarios here. How is dv dt related to dh dt if r is a constant? So we're going to hold the radius constant, and I'll do my best to draw my picture and communicate the idea of my picture. Then we're going to look how is dv dt related to dr dt if h is constant. So in the first scenario, the volume will change when the height changes, but the radius in this case is not going to change. Then we're going to look at the changes to the volume if the radius is changing and the height is held constant. And then we're going to look at the changes to the volume if neither one of them is constant. Both things change. All right, so here's my picture of a cylinder, and I'm trying to show you that the radius isn't changing. So that circle base is staying exactly the same, but the top of my cylinder is moving. All right, so just imagine like a can, and the can is growing larger. It's not growing wider, it's just growing tall. I shouldn't say larger, taller. It's growing taller. Right? All right, so here dv dt related to dh dt if r is a constant. If r is a constant, it's no longer a variable I have to differentiate. It becomes a coefficient of h. Right? Just like if I was differentiating 2x squared. Right? Y equals 2x squared, and we're going to differentiate with respect to x. Right? I'd have dy dx equals, I would just multiply, right? I'd take the derivative of x squared, which is 2x, and multiply it by 2, right? Just be 2 times 2x, which is 4x. We're going to do basically the same thing, because the pi is a constant, right? Pi is just a number. And if my radius isn't changing, it's no longer a variable. It becomes a constant too. And it's just a coefficient of h. Right? So volume is the area of our base times the rate of increase in our height. Okay? So now when we take the derivative, so here's my equation. Volume equals pi r squared h, and we're going to take the derivative with respect to time. The derivative of volume with respect to time would be dv dt. Okay? It just means the rate of change in volume over time with respect to time. All of this, I've got in yellow here, the pi, the r, the square, that's just a constant. It's some number. I don't know what the number is because I'm not told what it is yet, and it doesn't even matter what it is, right? Because I'm going to just treat that as a constant, right? And I would just multiply it by the derivative of h. Derivative of h with respect to time would be dh dt. Just like the derivative of y with respect to x would be dy dx, right? So notice here, this won't change. I'm still going to leave this as a quote unquote variable because it's got a letter in there instead of a number. But technically that's just a number. The pi, the r, the square, just a number. And as soon as someone tells me the radius, I can just plug that in, and if I know the rate of change in the height, I've got the rate of change in volume. Okay? Because my base isn't changing. The area of that base is not changing. All right, so now let's look at the second scenario. Okay? So now the height isn't getting it's not growing any taller, it's just getting wider and wider because the radius is increasing. All right, so now how is dv dt related to dr dt if h is a constant? All right, so now when I take the derivative of volume will be dv dt, but the pi, the h, those are just constants. So now all I need to do is take the derivative of this right here, the r squared. Right? So if I take the derivative with respect to time of r squared, that's just going to be 2r. But it's not a t, right? So since it's not a t, it's an r, I have to use implicit differentiation times dr dt with respect to time. Okay? So now my constants, 2 is technically a constant. We got it though if I'm using the power rule. The h is a constant because the height's not changing, and of course pi is a constant. Okay? So height's not changing, it becomes a coefficient of r squared. Okay? So r is a function of time, so we take the derivative with respect to time. The radius of our cylinder is increasing, so we're going to have a dr dt, but we're not going to have a dh dt because there is no change to the height. Right? It's just a constant. Okay? So you have to think in these problems what changes and what stays the same. Sometimes everything changes. Right? So how is dv dt related to dh dt and dr dt if neither is a constant? Right? So we have volume equals pi r squared h. We have to use implicit differentiation. Now they are both variables. R is a variable, h is a variable, and of course the volume is a variable. Okay? So now I've got two variables next to one another. Neither one of those, the only constant here is the pi. That means I need to use the product rule. Right? So u here will be r squared, and v will be h. The derivative du dt is going to be, we take the derivative of r squared, 2r, but then we have to take the derivative of r with respect to time. So that's dr dt. We have to do the same thing. Oops, I was hoping to separate them. They're a little close. Let me just move that over a little bit. All right, so v equals h. All right, so now we have to take the derivative of that, dv dt. The derivative of h is just dh dt. Okay? So now when we use the product rule, remember our product rule, we can squeeze that in. Product rule. Okay? So we have the first times the derivative of the second, and I'll write dv. I'll write v prime. So actually, so here, just to not confuse you, we got, because there's v, the volume. This is just u and v parts of the product rule. I'm going to just put u prime and v prime. So u, our derivative is going to be u v prime plus v u prime. Okay? Don't forget, you have to use the product rule if you have, if you're taking the derivative of a product. Okay? All right, so derivative of volume, of course, is just going to be dv dt with respect to time. Okay? And here we can see from my picture, the top is moving up, the radius is, this is growing in both directions, so it's getting fatter and taller. Right? It's a giant can. Right? Pi I pulled out, because pi is just a constant. Right? I could include that as a coefficient of r squared, or just pull the whole thing out and just leave it in front and distribute it later. Because that's what will happen either way. It's going to look the same whether I pull it out or whether I leave it as a coefficient in front of r squared. So I just pulled it out, so it's just one less thing in my way. Right? So the derivative of, let's see if I can use the same colors here. The derivative of r squared is going to be 2r. But we're taking it with respect to time. Okay? So because we're taking it with respect to another variable, we have the dr dt. Oh, and this one, for simplicity's sake, I took the derivative of the first one. So let me, or v prime u, or excuse me. Addition is commutative, so it doesn't matter which way these go. Whether I take, boy, am I using my v's, it's so much alike. Whether I take the derivative of the first and then multiply it by the second, and that's first, or whether I take the derivative of the second and multiply it by the first. So it doesn't matter the order here. U v prime plus v u prime, or v u prime plus u v prime. Okay, it doesn't matter who comes first, right? Sometimes on these related rates, I like to just take the derivative of that more complicated one first, which is the r squared. And that's what I did in this case. All right, so I took the derivative of the first, which means I'm going to multiply it by the second, right? That one's not going to change. So I've got 2r dr dt, and then times h, right? So that one doesn't change. It's I took the derivative of the first and then multiplied by the second. So now I've got to have the derivative of the second times the first one. So the r squared, and then times because that's not my, I've got to take the derivative of the h now, and since that's not, I don't have orange here, yellow. Since it's not a t, I have to use implicit differentiation, so dh dt. Okay? So the dr dt is the rate of change in the radius, and the dh dt is the rate of change in the height. So my derivative, and now I'm just going to multiply that pi in. All right, so I'm going to distribute the pi, is going to be 2 pi r h. Interestingly, it happens to be the circumference. That's the formula for circumference, but it is the derivative there, times dr dt, the rate of change in the radius, plus, I didn't change r squared at all, and when I distribute the pi back, I've got the formula for area, pi r squared, times the rate of change in the height. It's just a product rule. And initially, these may seem really complicated, but once you get the hang of it, once you learn to draw the pictures and analyze the situation, you'll find that they're not very difficult at all. And they they're sort of formulaic, but you got to think about it. You really got to, it's very, very important that you think about the problem first and set everything up before you ever try to solve anything. As a matter of fact, I didn't solve anything except for the first one. I didn't solve anything in any of these problems. I just set these up. And so you can see how we go about solving these problems. So in class, we'll start with a new problem. pumping out a tank, and we're going to use that volume formula, and now we're going to have some values in here and take some derivatives, okay? Because now we've got an actual problem here. All right, so see you in class. Bye.